Electricity is one of the greatest innovations ever made. And though there was a time that humans lived without this commodity, it is hardly possible to imagine how the world would operate today without this precious commodity. The production of electricity is generated in power stations that are far away from the load. That is why there are extensive conductors that are set between power stations and the needed consumers. Due to this fact, power loss in transmission lines is a common issue. The article will address power loss and how to reduce it. Different power is lost at different stages. 1–2% of energy is lost during the step-up transformer from when the electricity is generated to when it is transmitted. 2–4% of energy is lost in the transmission lines. 1–2% of energy is lost during the step-down of the transform from the transmission line to distribution. 4–6% of energy is lost during the distribution, so the average loss of power between the power plant and consumers ranges between 8–15%. In modern society, we cannot think to live without electrical power. In early days, electricity was transmitted by using direct current. After Nikola Tesla invented alternating current 1886, this electrical transmission gets much popular. Today we can send power through the continent by using this alternating current. Once the length of the transmission line becomes longer, the conductor resistance also gets the increase, so the energy loss is also getting increased. This problem of the AC transmission is much solved by using transformers to step up voltages. But there is another problem that occurs due to the impedance of the transmission line. Another external property called reactance also happen in this transmission lines, and this lead loss in the front too. This happens mainly due to the property of inductance and the capacitance of the transmission line. Inductors have commonly resisted the changing in current, and temporarily storing energy in the magnetic field. The capacitor is also opposed to the voltage differences and temporarily storing energy in the electric field. Transmission line losses are a major concern in electrical engineering, especially when it comes to efficiently distributing power from generation plants to consumers. These losses affect not only the overall efficiency of power systems but also the cost and reliability of electricity supply. Understanding the causes and mitigation strategies for these losses is crucial for electrical engineers and industry professionals. So, what are transmission line losses? Any power transmission system incurs losses because some power input is dissipated as heat. In AC transmission, the main culprits are the line's resistance, reactance due to inductance and capacitance, and corona discharge. These losses, known as transmission line losses, can range from 5–10% over long distances if not properly managed. The primary contributor to transmission line losses is the I²R loss, which depends on the resistance R of the line. A transmission line can be modeled using R resistance, L inductance, and C capacitance parameters. While L and C are energy storage elements, only R dissipates energy in the form of heat. Types of transmission line losses. One of the most common types of transmission line losses is resistive I²R losses, also known as copper losses. These losses occur due to the inherent resistance in the conductor material, such as copper or aluminum. As electric current flows through the conductor, the resistance causes heat to be generated, which results in energy dissipation. Reducing resistive losses requires using materials with low resistance and larger cross-sectional areas for the conductors. Another type of loss is corona losses, which occur in high-voltage transmission lines. When the voltage of the line exceeds a certain threshold, it ionizes the air around the conductor, resulting in energy being dissipated in the form of light, sound, and heat. This process is known as corona discharge. Factors such as high voltage, conductor surface roughness, and adverse weather conditions like rain and fog can increase corona losses. These losses are more prominent in AC transmission systems and are more common in extra high voltage EHV and ultra high voltage UHV lines. Dielectric losses occur in the insulating materials used in underground or undersea transmission cables. These losses result from the continuous polarization and depolarization of the insulating material in response to alternating current AC. Although minimal in most transmission lines, dielectric losses are more critical in cable systems and EHV systems that use oil or gas insulation. Another important category of losses is inductive and capacitive reactive power losses. Inductive losses occur when energy is stored in the magnetic fields of inductive components such as coils and transformers. Capacitive losses happen when energy is stored in the electric fields between conductors. Both phenomena result in the flow of reactive power, which does not perform useful work but contributes to energy dissipation. These losses are especially significant in long-distance transmission lines. In transformers and other electrical machines, eddy current and hysteresis losses are common. Eddy current losses occur when circulating currents are induced in metallic parts due to alternating magnetic fields, resulting in heat generation. Hysteresis losses are due to the repeated magnetization and demagnetization of magnetic materials, which also cause heat dissipation. These losses can be minimized by using laminated cores in transformers and optimizing the design of magnetic components. Leakage current losses occur when some current escapes the transmission lines due to poor or degraded insulation. This can happen in high-voltage systems where faulty insulation allows current to leak into the air or ground, especially in aging infrastructure. These losses are typically small but can become more significant in humid or moist environments. Skin effect losses are another type of loss that occurs at high frequencies. The skin effect refers to the tendency of alternating current AC to concentrate near the surface of a conductor, rather than flowing uniformly throughout the cross-sectional area. This effectively increases the conductor's resistance and contributes to higher resistive losses. The skin effect is more pronounced in large conductors and at higher frequencies. Harmonic losses are caused by the presence of harmonics, which are higher frequency components introduced by nonlinear loads such as rectifiers, inverters, and power electronics. Harmonics cause additional heating in conductors and transformers, leading to greater energy dissipation and reduced system efficiency. These losses also contribute to power quality issues and stress on electrical equipment. Methods to minimize transmission line losses. Several strategies can be employed to minimize losses in power transmission lines. One effective method is to increase the size of the conductor, which reduces resistance and, therefore, resistive I²R losses. Larger conductors, such as aluminum conductor steel reinforced ACSR or aluminum conductor composite core ACCC, are often used for their strength and lower resistance, especially in long-distance transmission lines. Another method is to use high-voltage transmission, which lowers the current for the same power level and reduces resistive losses. High-voltage direct current HVDC lines are particularly efficient for long-distance transmission because they eliminate the need for reactive power compensation that is common in AC systems. This results in significantly lower losses. To reduce corona losses, bundled conductors are often used. Bundling conductors increases their effective diameter, reducing the electric field intensity around them and minimizing corona effects. This is especially useful in extra high voltage EHV and ultra high voltage UHV systems. The use of flexible AC transmission systems FACS, such as static VAR compensators SVC or static synchronous compensators STATCOM, helps manage reactive power and improve voltage stability, reducing losses in the transmission system. In addition, power factor correction using shunt capacitors can compensate for reactive power and reduce unnecessary energy dissipation in the system. Advanced technologies like superconductors are also a promising solution for eliminating resistive losses entirely. Superconductors have zero electrical resistance at very low temperatures, making them ideal for long-distance transmission. However, their high cost and the need for cooling limit their widespread use. Smart grid technology is another important tool for reducing losses. Smart grids use sensors and real-time monitoring to optimize power flow, load balancing, and reactive power compensation. This leads to more efficient transmission and lower overall losses. Additionally, network reconfiguration helps distribute the load more evenly across the system, preventing overloading of certain lines and reducing losses. Finally, improving insulation and conducting regular maintenance on transmission infrastructure can help minimize leakage current losses and dielectric losses, especially in underground cables.